Okay, we are live. Hold on. Okay. Yeah. So, I am going to try to start uh a a regular stream every day if possible, or maybe every other day or something like that, where I work on interview prep, basically interview prep for upcoming interviews that I expect to have in the next couple of months. Hold on, the music is a little bit chaotic. Let me just yeah. So for this interview prep series, I don't want to call it a series because it sounds a little this makes it sound like more than what it is. It's just me studying on stuff and practicing some code on lead code and maybe different platforms. I don't know. Sounds like a good idea. Thank you. Yes. So I loosely speaking, I aim to do this about this time a day, whatever time that is for you. I'm sorry if this time right now is a very bad time for you. I don't know if there's somehow a lot of demand to do it in a different time. Maybe I will. I don't know. But for now, this is about right. Right now, it's about 10:30 p.m. for me. So maybe I'll spend like an hour and a half a day. The goal is not to really to do too much on this. It's just to be consistent. Even half an hour a day, I'll be happy. Yeah. So my goal is to do it consistently than to before I was thinking about any specific goals. So anyway, okay, enough of introduction. So the interview prep mostly the way I envision it will have three components to it. So my background is in statistics, and I'm interested in probably jobs in the statistics area or data science or machine learning or some tech related job. So as far as interview goes, I think there are three parts that I really want to work on. Can I just do this? Three. So first is the coding part, which is the data structures mostly, and that is what I'll be doing today. And then the next thing is also deep learning. So that's just I guess that's just a very popular popular type of machine learning that people like to do in the past decade or so. And I do know a little bit about it, but I haven't been a practitioner for the most part, so there's a lot that I need to get used to. So those take time as well. And lastly is probability theory. So that will come in handy for jobs related to the fintech or like funds, hedge funds, that kind of stuff, where it could be slightly more, a little bit more mathematical in nature. Well, even though arguably these types of jobs, they all are. Okay, so yeah, I will be jumping back and forth between all these things without any real sequence, I think. The goal is just to keep on doing and build a habit, rather than worrying about, specifically what am I supposed to do today. Okay, so today I want to do on data structures. I have a couple of sources, and I think a good way to start is just to get a refresher on the data structures that are very popular, and the standard ones, lists, queues, stacks, that sort of stuff. And so we'll be going through them today. And I'm reading this book by Steve Skeena. I'm sorry if I pronounced it wrong. The Algorithm Design Manual, Chapter 3. So if you have it, I don't know. If you have it, read along. I don't know. But yeah, that's what I'll be doing today. Yes, and then the nice thing about this book is that at the end of the chapter, there's there's links to lead code practices, problems that are relevant, and there's like 45 questions. So I won't be short of problem sets and things like that. Probably will not be able to even attempt half of them. But the goal again is just to get familiar. Okay, so let's see how far we can go. I think I really want to call it at midnight. If I don't get too far, it's fine. just want to call it rather than spend too much time and get too tired. And then and then just get burnt out of this habit before even building it. That would be unfortunate. Okay, what else? Anything else I want to say? I don't know. That's it. Okay, let me close off some of the other documents that I'm not using currently. Okay. So one last thing is, I guess I have come across these things before. I took a course in them a couple of years ago. Actually many years ago. This is many years ago. But interestingly, I do have some recollection of all these things. At least get a good sense of what they are fundamentally about, and then what I really need to do is practice and do some refresh. Okay, so I'm gonna go through this chapter if I can in this session. So let's go. So in this project, I guess I don't really plan to take too many notes. Maybe I should, but this is not my first time seeing these things, so I think it would be good to read them quickly and get a good sense from doing instead of just reading. And whenever I need to reference it, I can always come back to the text. But who knows? Maybe reading is maybe taking notes is completely necessary. So for data structures, I think most of them I'm quite familiar. The biggest one that is problematic is graphs, or maybe I don't know if those count as data structures, but graphs generally and the dynamic programming stuff gives me a little bit of problem. But let's start here first. Okay, contiguous. Okay, I don't think I really need to know all these theoretical stuff, even though I mean I'm interested, but I doubt they'll be super relevant in interview settings. Okay. Okay, just a little good introduction. Okay. So arrays are contiguous. Contiguous means that in the memory space they are next to each other. Right, that's the point. Wait, so it says that contiguously allocated structures include arrays, matrices. I should highlight at least, maybe. Contiguously allocated structures. I don't know. Hold on. Yeah. Arrays, matrices, heaps, hash tables. Wait, hash tables are contiguous? Okay. Linked are not, but they are bound by pointers. Okay, yeah. So contiguous, well, I mean, logically speaking, if they're contiguous, if they are in one space in the memory space, then it's easy to locate things relative to one another because we know that they are near each other. So that's because the index of each element maps directly to a particular memory address we can access instantly if we know the index. Okay, that's true. That's true. Space efficiency. Okay, so it's kind of light. Yeah, memory locality. What does that mean even? Okay, so yeah, so you get to use things like cache. And then yeah, constant time access given the index. And I guess it's space efficient. I don't know if you want to say that, but okay. The downside is that we cannot adjust their size in the middle. Okay, now we're into... Okay, hold on, the music is very distracting. Like, I get it, but dude. Okay. The downside of arrays, which is contiguous, is that we cannot adjust their size in the middle of an execution. Yes, okay. Program will fail soon as you try to add them by extremely large arrays but waste space, restricting what we can do efficiently. Dynamic arrays. Okay, I'm just gonna hide. Well, should I even bother highlighting these things? Okay. I guess I will, just for my own, I guess, markings. Suppose we start, we double m to 2m, run out of space. Okay. So this is a bit slow, right? It will take, wait, apparent ways in this procedure involves recopying old content, yes. So that when we double it, we need to migrate. And it's a bit of a waste. How much work do we do really? Oh, by the way, let me check something. Cause, boy. Cause I might not read the chat if there is anything at all, and I think in the settings now that the text disappear after a while, so I'm not sure if I can change that. And I apologize if well, I mean, so far there's no one, but there's one person I don't know. Okay, so the message will fade away after 2 minutes. Okay, I think it's active now. So if you type something, it should stay there for 2 minutes. And if I don't see in 2 minutes, then it's a bit unfortunate. Okay, let's keep on going. It will take log2n, also known as log n, doubling until the array have n positions, plus one final doubling on the last insertion when n equals 2j for some j. Until the array gets to have n positions, and one final doubling, plus one final on the last insertion. Forward, so 2j. What does that mean? So let's say we're talking about say 1024. It will take 10 doublings. So you start with 2, then to 4, to 8, to 16, 32, 64, 128, 256, 512. And then you have n positions plus one final doubling on the last insertion. Ah, okay, so at the end you double again. Yeah. The number of copies and the ith doubling will be 2i. Well, what? Ith doubling. So if it's the second doubling, then it will be, you need to copy us to. Okay, yeah. So the total number of movements. Ooh. See, I didn't read from the start, so I'm not sure if this is how the book is kind of prefaced. Like the way they're gonna discuss things is like this, like a but I guess just that's how it is. Okay, so n plus everything up to n. 1, 2, 4. Okay. Which is less than this. Which is less than this. What? Which is less than if you put infinite to it, and this is sum to. This sums to. Wait, what? Hold on. Oh, it sums to 2 because it starts from 0. Okay. Thus, each of the n elements move only 2 times on average. And the total work of managing the dynamic array is the same ON as it would have been if a single array. Ah, this is interesting. I mean, okay. Shoot. What do you mean move 2 times on average? So for example, the last thing will move once, and then this thing have to move like n minus 1 times, and then you add them all up. and then on average they move twice. So the movement is on average 2n, where each move twice. I guess the primary. Sometime in the worst case. Is the guarantee that in the worst case, note that all accesses and most insertion will be fast except for those relative few insertions that trigger array doubling. What we get instead is a promise that the nth element insertion will be quickly enough that the total effort will still be on. Such amortized guarantee arise frequently in analysis. Okay. We denote star P. Oh my god, pointers. Yeah, I remember pointers was the kind of if you take a first course in C language, the I guess the last thing you might learn about the whole thing could be either structs or something like that, or like kind of what memory stuff, or like I did, it was pointers. So the pointers is like the last thing you touch in the course of a beginner C course. And it's the thing that it just gives you headaches. Because it's a thing that points to a thing that's not necessarily a thing, blah, 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 blah. We use star P to denote the item that is pointed to by pointer P. Here we go. And ampersand X to denote the address of a variable X. And null pointer is used to denote structure, terminating and unsigned pointers. Links, linked list. Okay. Type def. Okay, so this is a struct. So this is in a C. This is like a C, I guess, imitation of a class. It's kind of, it's not really a class because I think you can't do most of the thing you can do with a class, but it does bear some semblance of what it is trying to do at least. Item type, item, struct, list, next, type def. Data item, and then you point. Okay, hold on. You point to the. Okay, hold on. This is the item that you're pointing to. Okay. So link list. Okay. Each node contain a pointer field to at least one other node. And so next is a pointer, but star next is what it is pointing to. And this would be the item, not the address. Okay. So the pointer holds the address of the star item, but the address of the pointer is not the same as the value that the pointer holds, which is the address. Or reference. I think that's the word they use in C. Reference. Each node contains a pointer field to at least one other node. Finally, we need a pointer to the head so we know where to access it. The list here is the simplest linked structure. The three basic operations, search, insert, delete, and doubly linked list points to both its predecessor and successor. This simplifies, but with a bit of, yeah, I need more space. Okay. Searching for a list. Searching a list for item X can be done iteratively or recursively. I opt for recursively in the implementation below. If X is in the list, it is either the first element or located in the rest of the list. Eventually, the problem is reduced to searching an empty list which clearly cannot contain X. Okay. Oh my god, why is this in C? Okay, doesn't matter, I guess. Okay, the problem with the C thing is that I need to recall a bit about like the function signature here. When you put a star, what does that mean? It means you feed in a pointer and then it takes in L. Let me just check that. So pointer arguments. Swapping two number using call by reference and yeah, there's pass by reference and pass by value. So okay, swap. Okay, so then you swap. This is swap by. Wait. Oh, okay. So temp A, B, B. Wait, but how is this called by reference? You're swapping the values, right? Here. Ah, okay. So when you do swap, you put the address. Ooh, hold on. You pass the address, which is the pointer. Essentially, you're creating a pointer in this case, I guess. You pass it to, then the pointer A holds, and to the address of M and B. Okay. Yeah. Okay. I think I can swallow that. Let me just double check to check pass by value. Okay. Okay, so pass by value means a copy of the data is made. Yeah, but how is that an example? Okay, pass by value. Here we go. So you void do it T, and then you pass by value by pass by reference. You have a T. Oh shoot. Okay, so here they use an N, not a star. So if you put a pass by reference, so if you put a Z, then do it Z, it will take the address. I suggest using a oh no. Oh wait, so this is C++. Oh, okay. So if it's C, then it's a star. Ah, I see. Oops. Yeah, C++. I don't, yeah. I once upon a time learned C++ and didn't really go too far and I forgot most of it because of how horrible it looks. And I know people love it because, it's good, blah, 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 but yeah. I don't think it's that popular anymore. And then so you put the address of Z. Cool. Okay. I'm glad I tried this thing before years ago and I have some memory of what's going on. Array always pass by reference because array is contiguous. So constant. Okay, blah blah blah. Okay, I think I understand. Okay, so this one means you put the it's passed by reference, then L. You just use L as usual, I guess. But in this case, changing L would change the original object because you're not passing the data, you're passing the address, which is accesses the stuff. Okay. If it's null, return null. If the item is equals X, return L. Else search list L next. So if the item is X, return the node itself. Okay, I got you. Insertion, maybe. Okay, maybe let's not look at. Why are there ants? Why are there ants on my table? Haven't had ant problems in a long time. What's going on? So okay, insertion into a list. Oh my god, can I? Is there a way to draw things here? I don't know. Whiteboard. Online. Ads. Whiteboard. Start. I don't know. Let me just start drawing. I don't have a tablet. Okay. Let's see how annoying it is to just simply draw something online. Okay, so you have a thing, it points to a thing, and then it has data inside. Say data is like this, it's just this black stuff. So to insert, what I mean is that I want to have something that I want to insert it to. And the insert is to link this, and then break this. So it's important to figure out what order we want to do this in. So because, for example, I can't link to this before I break this, right? Because I can't hold two successor at the same time. And so I cannot do this as number one. That's not possible. But if I do this first, if I break this first, then this will be lost forever. So what I need to do is do this first. Then break this. Then join this, I think. Okay, let's see. So you are given this thing, and then the item type. What's item type? Since we have no need to maintain the list in any particular order, we might as well insert each new item in the most convenient place. Insertion at the beginning of the list avoids any need to traverse the list, but does require to update a pointer to the head of the structure. Okay, so in this case, this would be like the head. Okay. So I think you built. So this is the new guy. Call it N. Yeah. So it will look like so n.next equals to head.next, and then head dot, I mean this is done in one motion actually, so head.next equals to n, something like that. I don't know what malloc is. I mean it's a memory allocation, but don't remember details. Hey Shiro, how are you, man? So list star L temporary pointer. Wait, what is double star? Keep on forgetting. Doing well. Good to hear. Good to hear. Yes. So double star, declaring double pointers. Oh, so it's a pointer to a pointer. Okay. Yes. How's your PhD going? Well, thanks for asking. It's going. So it's about crunch time. I'm about to really crunch hard and try to put the thesis together in the next 2 or 3 months. And at the same time, now I'm doing a bit of interview preparation. Yeah. Okay. So this is a pointer to a pointer. Okay. I guess I can work with that. But does require us to update the pointer to the head of the structure. Does require us to update the pointer to the head of the data structure. So p.item temporary point. Oh, you need a temporary pointer? Oh, because... Is it because... Oh, hold on. Any reason you're doing it in C? No, this book is in C, so I just I was recommended this text, and it happens to be in C, and yeah, so no real reason. I don't really use C, but I mean, might as well practice it a little bit. So I guess it's because there's a hit here. This is and then you need a pointer. Maybe our visualization of a pointer is not even correct. So this is a pointer that points to here. And then so I need to point this to this now. But what's the difference to... Wait, linked list in C. I just look at a picture to see what people usually draw it out like. Yeah, so you can just say that it's a hit, right? So there's just an arrow here. Okay, so what I have is more or less correct. Aha. Okay, yeah, so it's just a hit. Then you want to... Oh, no. Yeah. Because... Oh, hold on. Whoops. My bad. Can I just... Wait, hold on. I'm just gonna move everything. Okay, let's just restart over here. I don't know. So you have, let's say this thing points to this thing, points to this thing, and then you have here, and then this is your hit pointer. And then if you want to insert at the front, what you need to do is point this here and then change the hit to point to here. This one goes away. Okay. Yeah, in this case you can do it however you want, right? You can just do this first and then no, hold on. You need to hold on to this first. I guess that's how they use the temporary one. Yeah, so the temporary pointer, the item would be X. Point the pointer to a pointer. So this is the hit, right? Okay, so L is a pointer to the hit, and then you are yep, here we go. Let the confusion begin. So L is a pointer to the hit, and then so if you star L, you get the location of the hit. If you star L, you get the location of the pointer, which is the location of L. No, yes, no. Yes. So p.item, you point to X, and then L.next point to... Wait, what? What? Whoa, I don't even know what's going on. Wait, so this is not what you want to enter? No, correct. So it says here your... Maybe I can do them side by side. Okay. Okay. Whoops, shoot. Can I delete everything? Clear. Nope. Come on, man. Don't make it hard. Oh, okay. Okay. Let me just move it out of my side then. So you have the L points to the head, and then what you want to do is that you have X, so you want to wait, I don't understand, why can't you just say something like so maybe X dot next given to L dot no, just L, right? Yeah, just L. Oh, star L, sorry. Right, star L. Oh, correct. Wait. Yeah, but why do you need to do the temporary stuff? So you're saying that I have a P and then the item is X. Oh, X is a value. Ah, I see. Ah, so it's not a node. Okay, so you create a node, then you store in it X, and then you say that P.X equals L, and then L equals the L star L equals to P. Yes. So the address of L, I mean the address that L holds is now, or rather L now points to P. Okay. Okay, I mean, I'm not paying too much attention to this because I'm sure I'm gonna mess it up and come back to it later. Deletion? Okay. So you need to delete. It's a bit more complicated. Let me just try to draw it out on my own paper. Let's say I want to delete this guy. I need to find the predecessor and then point to directly the deleted item's successor. Okay. Item ahead. Okay, so this is just to look for the item ahead. The predecessor is needed because it points to the doomed node, so its next pointer must be changed. The actual deletion is simple. Once ruling out the case that the to be deleted does not exist, special care must be taken to reset the pointer to the head when first element is deleted. I understand that. Okay. Okay, let me not look at this. Okay, let's just see what we have here first. It's just gonna be a mess. Delete list. Delete list. Maybe you can try something else here. So online notepad, memo notepad, sure. Oh, I used this before. Okay. So to delete list, I need the list, which is the pointer, and I'm always using reference. So if I want a pointer, I need a pointer to a pointer, and then I need the value of the item to be deleted. So wait, X. Wait, why is it double star X? Let me think. X is the, wait, so this is also a list. So this is also a pointer. Okay, so let me try to draw it out. So L X. Do I need to use the item ahead? Okay, so assuming item ahead gives me the, if L dot next give me X. So I have my predecessor goes to, just let's say I put, no, I put in shoot, oops. Was it X? I don't know. Let's say I put in L and then X. Of course it's not, it's star L and star X. Why the X is the actual node? No, X is the pointer to the node. Get it in my head. X is the pointer to the node and L is the pointer to the start of the list. And then I get, what do I get back even? I get back L dot, if L dot next, I get the node. So pred is node. And then wait, hold on, let me check something. So it has a pointer. So next is the pointer. Yeah, I'm gonna be lost in this, but whatever. Insert. Delete. Okay, it doesn't matter. Okay, so if I have the predecessor, then my predecessor is a node. No, which is a pointer, right? God damn it. This now suddenly becomes a practice in C. There's really not the point here. Okay, so if I can't do this in the next 10 minutes or next 5 minutes, then I give up. Fine. I mean, yeah, I've not used C in a long time. Suddenly I'm jumping back into this, so it's not very surprising that I'm having trouble. Why is that a star, by the way? Why is that a star, by the way? What? Yeah, like this. Function pointers. But of course, I forgot about them. Wait, hold on. Hey bro, best of luck for the interview. Thank you. I'm not, I'm not exactly preparing for a specific interview, but thank you. Yeah, I plan to be applying quite a bit in the coming months. So yeah, I do need the luck. I think feels like a competitive market. I don't know. So PC equals to the address. So PC is a pointer, and then TC you store in it the address of the variable C, and then so when you what's the word, dereference it? Oh, I forgot what's the word, but when you star it you get the value of the item in the address. Yeah, so now if you store that equals 1, we have changed, since PC and the address of C is the same, C will be equals to 1. Okay, now this is easy, right? The problem is when you use with functions and stuff like that. Yeah, let me just do a quick read up on that, so that, I mean, okay, this is really not the point of this exercise, but okay, whatever, I'm learning still. Who knows, maybe the interviewers will be asking about pointers. Granted that it is one of those things that probably trip people up, especially during high stress situation. I'm not sure if I can do all these things with a person staring into my eyes. So this means it expects a pointer, and if I use n1 it will be the pointer, and I star n1 it will be the value. Okay, it's actually not terribly complicated once you see it, but a pointer to a pointer is when it gets a little bit confusing, right? A pointer to a pointer, that means the pointer has the address of another pointer. So if you star a double pointer, you get the original thing. Okay, I guess it's not that bad. Okay, let's keep on going. Okay, I can do this. Let's go. Okay, so search list. So L equals to hit node. No. Pointer to hit. X. Pointer to doomed node. Can we make this bigger? I don't know if... Yeah, okay. Okay, so insertion, deletion from list. You need to look at hit, item and hit. So let's say, okay, so item and hit expects expects a pointer. Wait, why do you use a double pointer though? I don't understand. Pointer to the pointer to a list. Why? Thus the last variable copies P, which is a pointer, to the place pointed by L. which is the external variable maintaining access to the head of the list. Okay, whatever, man. Okay, so delete list, you have a double pointer, and then you have a, okay, let me just copy out this part first, see if I can get it right afterwards. I'm not gonna be following the syntax, I just wanna get it done. So if I'm wrong, don't yell at me. Okay. So this is a pointer called the pred, and then is a pointer pointer to node, and p item pointer. Okay, so to delete from the list, I know my pred already, my predecessor node, which is here. And then what I need to do is to take the x so p dot next equals to pred dot, it points to the node, something like this. And p dot item equals to star x, and then my predecessor p, I don't know, something like that. What? Oh, this is splice out of list. Wait, pred. Wait, why is it pred dot next? Ah, shoot. I don't think I have a good understanding of pointers. Pred dot next star x. Shoot. This is so annoying. Maybe it's the same thing. Wait, let me just try to look carefully. I think I'm being too hasty here. Okay, so a list is defined as it has item and it has next, and then the next
Okay, let me read this here. A linked list node. So this means to say that the node has a value and then also has a pointer called next. So the pointer is called next. Let me talk to a friend. Ask a friend. Because I have a bit of trouble understanding. So if you have, let's say, the pointer to the head, sure, right? But if you then do a star of that pointer, what do you get? I'm not sure what you get. Okay, this is about linked list. Wait a second. Okay, so one of the problem right now is I didn't understand that the arrow is not the same as the dot. I thought they're the same thing. x equals to something like this. So Goes to evaluate elements. So it's a pointer, then my head. Pointer to next equals to L dot star L. Your ls outside the function is now still the old one. It's because I passed by value. When I see star star L. Hmm. Pointer to list. Yes. uh, okay, it's quite good. I'm talking to a friend and it's very, very helpful. L star L star L. The hit, we want to change the hit. T is a pointer, and then the pointer the next would be star L dot. The pointer pointer Wait, so L is pointer to head node. Style is pointer to head node. So the star. So create new node. Step 1, create new node with node. Create new node pointer with node P. Step 2, give node. So it will be step 3, let point head. Point head. Point Oh shoot, it's almost midnight. Oh my god, and I've moved like what, 5 pages? God freaking. Okay, but I got this done. Pointer. Uh, you pass in the size of the data type as parameters too. No. If we have void star f arguments, function pointers. Wait. I use the term container to denote an abstract data type. Abstract data type, the primary storage and retrieval of data items independent of content. By contrast, dictionaries are abstract data type retrieved based on key values of content. Key values or content that will be discussed. Containers distinguished by retrieval order, blah blah blah. Stacks. So stacks is like stacks is like a like a stack of potato chips. The top one is the last one that goes in, and the first one that comes out. Push means put it on top of the stack. Pop means return from the top of the stack. Okay, this is understandable. Queues is, well, like what's a good example of a queue? Like a gun. Like a gun, I guess. Okay, well, not exactly. Kind of, where you put the bullet in at the back and then the ones that are inside comes out first. So first in, first out. Okay. So put. Get means get out the first one. Put means put at the back. And queue on queue. And DQ. Return a pointer to the element in dictionary D. Return a pointer whose key value is K if one exists. Return the pointer to the element whose key value is K. So if I have let's say that I have a dictionary of I don't know, let's say horoscopes, and then the horoscopes are the keys, and then the values are the date ranges and the dates in for the horoscope. So if I search for the key Gemini, that means I will get a pointer to the data, and the data is the set of dates, something like that. largest, smallest key. Oh, it's a priority queue. Whoa, hold up. Oh no, this is bad. Why did I do that? Delete. Give a pointer to X. Wait, give a search key, return a pointer to the element. Given the data item X, add it to the dictionary D. Given the pointer X to the given data item, remove it from D. Retrieve the item from D whose key is immediately before or after X is in the sorted order. Okay. Insert, cert, delete, successor, predecessor, minimum, and maximum. So this would be of a specific element whose key is item X. So this is item X, this is item X, but this is the pointer X to an item. Why gotta be like that, bruh? Why gotta be like that? Okay, let's see. Let me write down my solutions to see if I am kind of. So let's talk about so unsorted and sorted. Search. So for search, I mean, okay, let's say task, and then this would be unsorted, it'd be sorted. So search, if it's unsorted, of size n, I assume, it will be n, I mean on, I mean, let's call it n. And then if it's sorted, it will be log n. Insert. Insert. What does insert mean? Insert where though? Does it say insert where? I guess one, I don't know. I don't know. Sorted. I'm not sure what this means. Okay, wait. Insert. I don't know, insert should be just one, right? Delete. Well, you have to search for it first. Successor. Same thing. Predecessor. Same thing. Minimum. Maximum. Okay, that's my guess. I don't know. Let's see. Ah, no, it's sorted already. It's one. Okay, so this is correct. Wait. Ah, because you need to go. Wait, hold on. Why is it N? Wait, what? Okay. Insertion, incrementing N, and then copying item. So this takes constant time, yes. Deletion. Why is it 1? We are given a pointer X to delete the element, so we do not spend any time searching for the element. Ah, oh, okay, so it's by the, okay. Because we're giving the pointer to the element. Wait, if you're given to the pointer to the element and it's unsorted, oh, so you just remove the value. What? Wait, let me play today's Wordle. Okay, let's play some Wordle. Okay. Let's go with let's see. Let's go with arise. Boom. Okay. I guess I could start guessing, but I'm a bit too lazy, so let me just guess another. Okay, let's think. So there's an A and there's no I and E. A can be anywhere. And there's no S, so, and there's no R, so something like T might have some issues appearing. Or TH maybe? Okay, maybe let's try something like this. Oof. My luck is good today. I'm sorry if you're watching this and you haven't played it. Look away. Okay. I mean, there's not too many options at this point, isn't it? Hulk, chalk. I mean, god damn. So it's not shack, it is whack. Hey. deletion. Okay, no more Wordle. We are given a pointer of the element to delete. So we need not spend any time searching for the element. But removing the X element from the array leaves a hole that must be filled. Okay. We could fill the hole by moving each of the element from a plus 1 to n down one position, but this requires O(n) time when the first element is deleted. The following idea is better. Just overwrite ax with an and decrement and... Oh! Smart. Okay, it's a bit... okay, I kind of... so if it's insertion, I need to look for it. Oh, but why isn't... I'm looking for the pointer. Wait. Because... Wait. But why deletion would need... Okay, wait. Insertion gives us the thing. Why is it O(n) though? Insert. Given data added to dictionary. Oh, because you have to shift everything back, is that what it is? So n plus log n. And then for delete, you are given the pointer to what you want to delete. So you are given a pointer, and to delete it... Oh, because you have to shift it, is that what it is? Oh. A bit confused, but okay. A singly list unsorted. Okay, let me try to do it now. So this will be single unsorted double single sorted double sorted. So to search for something, single unsorted would be n. Double... Okay, wait. So search given... Wait, that means this is given key. Return pointer. Okay. And insert. Delete. Given pointer to data x. Successor. Minimum. Okay, now we are ready to discuss. Oh shit, I don't look at answer. Okay, hold on. So for a singly linked unsorted list, if it's unsorted and you want to search for something, I guess you go n. If it's doubly unsorted, I think it's still n, because you still gotta do one pass. If it's single sorted, it's 1, double sorted, it's 1. For insertion, okay, to insert, as we discussed, it's 1. Double unsorted, it's 1. Single sorted, it'll be if you're inserting into a sorted list, wait, it's not 1, right? You're given the key. You're searching through a single sorted list. Okay, so now I can only move back and forth. If it's sorted, I feel like it's still n, but on average it's a shorter n, yeah? I feel like it's still n. Yeah, it's still n, okay. Insert. To insert something, you need to look for it first. And then the insertion is 1. To delete something, it is gonna be 1 across the board because it's just cutting things around. Oh no, but you need to look for the predecessor, right? Yeah, so it's gonna be n. And then successor, it's gonna be n. Predecessor. Oh no, doubly linked list. Wait. If it's unsorted, you still need to find where it is. But for doubly unsorted, it's gonna be 1 here, and it's gonna be 1 here. Predecessor. Minimum. And no, single sorted, you still need n to get to the n. No. Maximum, you still need. You need to go all the way to the end, yeah? Okay, I don't know if this is correct. Let's see. Okay, let's check our search insert successor minimum. Okay, single unsorted. N1, N. Wait, minimum is 1? The heck? Okay, wait, what about sorted? N, 1, N. Nope. Successor is 1. Doubly sorted? N, 1, N, 1, N. and it's all 1 at the back. What is happening here? And double unsorted, N1, 1, and then N. Okay, that's the only one I got correct. So the rest is kind of wrong. Yes. Yes, insert. Okay, insert. We got it right. Search is correct. Delete. Delete is correct. Successor though. Why is it 1? Because we are given the item, right? Not the pointer, right? Are we given the pointer? Retrieve from the item whose key is immediately before of the item. Wait, what? We are given not we are the process. The logical successor is equivalent to the node successor for both types of sorted lists. I don't understand. So you're given the node, is it? Are you given a pointer? By overwriting the contents and deleting its original successor, we can delete a node without access to its list of predecessors. By overwriting the contents of the node to delete. Oh, okay, it's a bit of a cheat, but okay. Wait, but successor, I don't understand. Because you're given the data, don't you need to search for it? So you're given the pointer, is it? Doesn't retrieve the item whose keys. So you're given the item. You see, because you see a pointer X, but this is data X or item X? This is just item X. Why would it be constant time? I don't understand. What about here? Oh, so that means if it's a sorted, we will get time that is 1. Okay, I'm just gonna assume that okay. So yeah, if it's min... So successor, predecessor, I understand that the successor can always be done with 1, but the predecessor has to do with n because you would still need to find it. So n and n1, and then this would be n and 1 1. Yeah, okay. Minimum. Wait, why is unsorted 1? How? The minimum is at the tail. Okay. However, we can maintain a separate pointer to the list tail, provided we pay maintenance cost. The tail pointer can be updated in constant time on doubly linked list. On insertion, check whether next last equals to null, and on deletion and on deletion set last to null to the point of to the list predecessor of last if the element is deleted. Okay. Wait, what? We have no efficient way to find this predecessor for singly linked list. Wait. We can have a separate pointer to the end of the list. The tail pointer can be updated in constant time on a doubly linked list. On insertion, so if insert, check whether the last .next equals to null. And on deletion, set last to the point, set last to point to the list predecessor of last if the element is deleted. So last. Yeah, okay. Okay. We have no efficient way to find this predecessor for singly linked list. So why can we implement an O1? The trick is to charge the cost to each deletion, which already took linear time. What? Adding an extra linear sweep to update the pointer does not harm the asymptotic, while gaining us maximum in constant time as a reward for clear thinking. What is it talking about? Huh? What? Well, we can impede. Well. So if I'm telling you I want to find the maximum of unsorted list, you're telling me you can do it in O1 because you assume a deletion is done before that? I don't understand. The tail can be updated to each deletion. What does it even mean? So we assume we are doing deletion? Adding an extra linear sweep to update the pointer does not harm the asymptotic. What? I really don't get this. Huh? What? Wait, am I understanding things wrong? It sounds like it's trying to say. Wait, what is it trying to say? Delete is delete what? Minimum is minimum what? Why are they why is it related? What? Maximum. Minimum. What? 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 I don't get this part. What? Oh my god. Makes no sense. What is it talking about? What? So I have a singly linked unsorted list. What? The minimum element sits at the head of a sorted list, so it's easily retrievable. Yes, it's O1. The maximum is at the tail of the list, which normally requires O(n) time to reach in either singly or doubly linked list. Yes, however, we can maintain a separate pointer to the list tail, provided we pay the maintenance cost for this pointer on every insertion and deletion. The tail pointer can be updated in constant time. Yeah, just make sure that they always point to the tail, and you just watch out for that. So that means to say we can find max and min in constant time for everything, right? I don't know what this means. What? Uh, Then your delete is gonna be on. Oh. Wait. Oh. 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 Ah, it's already Wednesday. How did that happen? How is it already the middle of the week? I just started last week. I just started the week. It's ON because You delete. Delete. But if you delete the max element, you need to search for the biggest element. That's when one's sorted. So even if it's assorted, deletion. O1. Mm. Yes, but worst case. Search for the largest. Hmm. Interesting. Interesting. Damn. Wait, it talks about okay. Yeah. Okay. Okay, we are way over time. How far am I till I'm remotely close to being done for the chapter? Let's see. Yep, computer hanging. Very good. What the heck? What? I just want to change the view. Is it so hard? Screw it. Square root and elements. Okay, whatever. Yeah, I'm not gonna be done with this today. Okay, well, I mean, okay, well, not bad. I mean, I have learned a lot. Okay, so let's continue another day, and yeah, let's keep this up. So today, how far did I go? From I learned about the list and the speed at which you can do the things, queues and stacks. Even though I've already, I mean, I still need to have a practice session to really work with them. And I did a more or less quite a thorough relearning of the pointers, and yeah. Okay, cool. You know, it's what it is. I don't mind it. So if you have been, thanks for watching. If not, I mean, yeah, we'll be back and with more interesting data structures content. All right, see you guys. Have a good one.